We're told here that we have a gas contained within a piston cylinder assembly as shown in the image here. So here's the gas, here's the piston, cylinders, this part. And we're told it's initially at a volume of 0.1 cubic meters, but then undergoes a constant pressure expansion. So constant pressure is important here. At 2 bars absolute to a final volume of 0.12 cubic meters while being slowly heated through the base down here. The change in the internal energy of the gas is 0.25 kilojoules, so that's the internal energy in here. The piston and cylinder walls are fabricated from a heat-resistant material, so that means that we don't have to worry about any heat transfer through the piston surface and the walls here. The only heat transfer is coming in from the base. And the piston moves smoothly in the cylinder, so there's no friction with the walls here. Local atmospheric pressure is 1 bar. It's right up here. And for the gas is the system, so that means we'll draw a dashed line to indicate that the gas is our system here. We're asked to evaluate the work done by the gas and the heat transfer into the gas. Okay, so we're trying to find the heat transfer here, and we're trying to find the work done by the gas on the surroundings, which would be PDV work, because the only work that's going on here is the work against this piston face as we expand. So to find the work done by the gas, since it's PDV work, it's going to be the integral as we go from the initial volume to the final volume of PDV. And since the pressure is constant, we can pull that outside the integral, which just gives us the pressure times the final volume minus the initial volume. Now we're told that the pressure in the gas is 2 bar, so we can plug that in here. So this would be 2 bar. It's absolute pressure. The final volume, we're told, is 0.12 cubic meters, and the initial volume was 0.1 cubic meters. So we can go ahead and plug in those numbers, and what you'll get is the work done by the system, which is our gas here, is 4 kilojoules. Okay, so that's the first part, evaluate the work done by the gas. Now the heat transfer into the gas, the way we're going to find that is we're going to apply the first law to the gas. The reason I choose to use the first law is because we now know the work done by the gas, so that part we know. We also know that the change in the internal energy is given, and so if I think, how are these connected? Internal energy, the work, and the heat transfer, they're all connected via the first law. So I'm going to apply the first law to that same system. And let me write the form of the first law with it being minus the work done by the system, since I'm doing the minus work done by the system since we just calculated that a moment ago. And what we're trying to solve for, of course, is the heat transfer into the gas. So the work done by the system we just calculated was 4 kilojoules. The change in the total energy of the system, we're told that up here, we're told that the change in internal energy is 0.25 kilojoules. Now, if you look at the gas here, the kinetic energy is not changing. It's all 0 because we're told that it's being slowly heated at the base and the piston moves smoothly. We're going to assume that this is moving in very, very slowly so that there's really no change in kinetic energy. In addition, we'll assume that the change in potential energy is negligible as well. In fact, it's not 0, because since the volume is changing, that means the gas is expanding upward, and so its center of mass is moving upward, so there is some change in potential energy of the gas, but it's going to be very, very small, very likely. The density of gas is quite small, so when you calculate mass times gravity times the change in elevation, it's quite likely to be a very small number. So it's an assumption. So this would be the change in the internal energy then of the system. We're assuming that change in kinetic energy and the change in potential energy are both 0. So the change in the internal energy of the system, again, we're told is 0.25 kilojoules. That's coming from right up here. Okay, so when we then plug in the numbers here and work out the heat transfer into the gas or into the system, that'll come out to be 4.25 kilojoules. And that's it. That solves everything we were asked to find in this problem, so we'll end it there.